So, we talked about several applications of transistors. The last one was a transistor as a switch, and I mentioned that it is very important switching from high value to low value to high value in digital electronics. So, we will talk about digital electronics in next few lectures, but today I am going to talk on another application of transistors, and that is transistor as an oscillator. Okay. So, transistor in oscillator circuit. So, what is that oscillator? Oscillations, everyone knows oscillations, and the one which oscillates is oscillator. But in this context, in this electronics context, oscillator is a circuit or an instrument which converts DC to AC. That means you have voltage which is DC, you have batteries, you have cells, the voltage is DC, and you need AC voltage, alternating current voltage. So, to create this alternating current voltage from a DC battery or batteries, that is the job of oscillator, right. The power that we get in our household, 50 hertz to 20 volts, that is AC, but that is at 50 hertz fixed, and that is generated in the power plants. But for many applications, we need alternating currents, alternating current voltage or source with a desired frequency and a desired amplitude. For example, if you think of transmission of information, so what do? That information is mixed with carrier wave or carrier waveform, and that carrier waveform frequency is high in megahertz. Okay, so we do not have to, we cannot use 50 hertz AC supply as a carrier wave for transmission of information in the form of electromagnetic radiation. So, we need a supply which can give us alternating current voltage which changes as a function of time at frequencies of megahertz or hundreds of megahertz or gigahertz, like that. Similarly, many of the material properties, they are decided by the frequency, the electrical properties. For example, dielectric constant. Now, dielectric constant is a function of frequency, and we need materials which behave in a particular fashion at a particular frequency. So, to study those things, to make new materials, we need sources which can give us alternating current voltage at several frequencies, so that I can tune the frequency, I can change the frequency and do my experiments. Likewise, so the circuits which are used for this kind of thing, conversion or creation of that alternating voltage source from DC, so those are oscillators, oscillator circuits. So, depending on which frequency range I am interested in, whether it is an audio frequency range or it is in kilohertz, megahertz variety, or if it is 100 megahertz, gigahertz variety, different kinds of circuits are used in different regions. But what is common is we need a part, we need a unit which can selectively filter a particular frequency, the desired frequency, and can oscillate at that frequency. So, I need some kind of a circuit which once started, we do not give any external AC of that frequency, but by itself it can pick up a frequency, and at that frequency voltage or current in that unit should change, should oscillate. So, that kind of circuit, frequency selective circuit, that should be one essential part. Okay. So you have let us say you must have a frequency selective circuit oscillating. Frequency is oscillating anyway, so this kind of thing should be there. One can have varieties of circuits depending on which range you are. One is what we call inductor capacitance LC circuit. Okay, so you remember your high school thing. If you have an inductor, there is a symbol for inductor, and the letter which is generally used is L, and then you have a capacitor. Let us say you have a capacitor, and then there is a, okay, from here I can, alright, let me join it and put it here, a switch, and let us say this is a battery. So if I join it here, the capacitor is charged, C, capacitor is charged. And then if I remove it from here and connect it here, this charged capacitor, which already has a charge Q, plus Q here, minus Q here, so that will send a current, and you will have a current in this. So that is your LC circuit. So after charging through this battery, we just disconnect it and leave it here, and here you have a current, and this current oscillates at a particular frequency, right? If you go by equations, since the current is here, and as the charge gets transferred between these two plates, this Q is decreasing, and the rate of decrease of Q is also changing. So the current is also time dependent, and hence you have a back EMF in this inductor, and that back EMF is minus L di dt. So that's the kind of voltage that appears here, and the voltage that appears here on the capacitor will be Q by C, and since these 2 points are same, this point and this point is same, this point and this point is same, this minus L di dt should be equal to Q by C. And from here you can work out how this current will change in time. So if you differentiate, this is minus d2i dt square is equal to dq dt, and then this 1 by c, which is I by c. You take I on this side or take L on that side, you have d2i dt square is equal to minus 1 over LC I, and this if you write as omega square, then d2i dt square is equal to minus omega square I. So this is how the current will change in time, and this equation is familiar to you. This is a simple harmonic motion equation for a particle which goes in SHM. For that, the equation is d2x dt square is equal to minus omega square x. So that is for SHM, and you know the solutions, particle going in SHM, it just goes from minus a to plus a with some kind of an equation, which is, let's say we can write x is equal to some a sine omega t or cos omega t plus some constant. So that constant depends on the choice of t equal to 0, but essentially this is an oscillation. X oscillates in time, and exactly same is the story with this equation here. The solution of this equation will be I equal to some constant, you can write it as I naught, and then sine of omega t plus phi. So the current oscillates in time. It goes from plus I naught to minus I naught. So that means what will happen physically? Physically what you have is the current goes like this, and then it changes its magnitudes as a function of time, and finally it changes sign also, and it goes up to minus I naught. So it goes this way, and then it goes this way, and then it goes this way, and then it goes this way. So that means when this charge becomes 0, if the current is this way, then you are neutralizing this charge. Electrons actually are going from this plate to that plate, and hence this Q is decreasing, and then it becomes 0 at certain extent, and after that it is reversed. So the current still goes in this circuit, and this becomes negatively charged, this becomes positively charged, and the magnitude will be minus Q here and plus Q here, and then the cycle will repeat. If you think in terms of energy, this energy is electrical energy here is Q square over 2C, and the magnetic energy, which is largely confined in this, is half Li square. So as a function of time, this if this is the maximum Q, then the potential energy, electric field potential energy, will decrease, and this will increase. The total will remain the same. This magnetic energy plus electrical energy, that will remain the same, but then it will oscillate between the two. This Q will decrease, so the electric field energy will decrease, I will increase. So this okay, let me write small I. So this magnetic field energy increases, then later in the cycle this will decrease and this will increase. The total remains constant. As in SHM, kinetic energy and potential energy, they are exchanged between themselves, and total energy remains constant. So that's the kind of oscillations. But then if you use this in some circuit, if you want to make use of it, you can take any potential here, voltage. This voltage is oscillating in time, so you do have an oscillating voltage, but then if you want to use this oscillating voltage for some kind of a circuit, you want to connect it to some external unit, then this energy is not going to remain constant, and if you are using that energy, that means this oscillation will die out. And even if you don't use it for external purpose, even internally it does have some resistance, and if it has some resistance, then this equation is not going to work, because you have another R into I, resistance into I term in the equation, and power is dissipated there, energy is dissipated there, the current is going to be, so if you have resistance, then this current will be going to be some e to the power minus beta t, and then sine of omega t plus phi. This omega is slightly different from this omega which is here, which is here. Omega is, okay, what is omega? Omega square we have written for this. So omega is square root of 1 by LC. So if you have resistance, it could be slightly different from this, but nevertheless the important point is here. The important point is here, it will decay, the amplitude will decay as a function of time. So if you want to have a source of alternating current, alternating voltage, which changes with time in that fashion with a constant amplitude, and you are using it for external circuits, you are taking power from this, still it maintains that, then you need to do something else. You have to compensate for that power which is either lost or which is used externally. And hence in this oscillator, to design the oscillator, you need some amplifier where part of the signal is amplified, and then part of it is again sent to this oscillating circuit unit, so that whatever is lost is exactly compensated, and then you have a constant voltage supply. So that is the other part. So together with this frequency selective oscillating circuit, you need an amplifier, that's one, and then part of that amplified signal or voltage must be brought back and added to this oscillating circuit. So the block diagram will be like this. This is your frequency selective. Why frequency selective? Oscillating circuit. Because we are not providing any frequency from outside, we only have batteries, and therefore this system must decide its own frequency. Like in our LC circuit, if I put certain millihenries of inductance and certain microfarads of capacitance, then we have fixed, the circuit has fixed, this is angular frequency. Okay. So there is a particular frequency at which it will oscillate. Therefore, you need this frequency selective oscillating circuit. And then you need an amplifier. This signal has to be amplified, and this is where the transistor comes into picture. It needs to be amplified. And then this amplified signal, you can take your output also from here, use it for external world, and part of it should come back and add to this oscillating circuit, otherwise this is going to die out, these oscillations are going to die out. So you should have another unit in this whole arrangement, which we call feedback circuit. It takes part of this signal which is here, amplified signal. You can take it from here, you can draw it like this. So part of that output signal is taken, and then that part is brought back and added to this. And remember, this addition has to be in phase. You already have an oscillating current or oscillating voltage here, and then you are adding, which is again oscillating thing. So you are adding two sine waves, let us say, or two sine wave forms. So they have to be in phase, then only there is an addition. If they are out of phase, then there will be actually a subtraction. If you have some y1 which is a sine omega t, a1 omega t, and then you have y2 which is a2 sine omega t plus something else. So it's important that this, if you want actual addition of amplitudes, actual addition of that oscillations, then they should be 0 or 2 pi. So that it is just a1 plus a2. If this epsilon is 0, then your y1 plus y2 is just a1 plus a2 times sine omega t. So amplitudes are added, signal has enhanced. But if it is not, if suppose epsilon is pi, in that case sine of omega t plus pi is equal to minus of sine omega t, and then in that case y will be equal to y1 minus y2. Actually it is y1 plus y2, but this will be a1 minus a2 times sine omega t. So your amplitude has actually decreased. So it's important that this signal which you are adding to this oscillating circuit, that should be in phase, known as positive feedback. So essentially this is the thing which has to be implemented. Circuits are made to do this kind of thing, and the transistor actually comes here, right. So, before going into the circuit that can be used as an oscillator, let me show you the action or an oscillator in actual performing on the table. So, let's look at this. So, this is the unit which is oscillator, and we are giving it to power, we are giving it power from this supply. I told you that the function of oscillator is to convert DC into AC. So, we need DC voltages, but still we are using that power 220 volt and 50 hertz. But that is because we do all our DC conversions here in this unit itself, otherwise we will have to carry batteries, etc., etc. So, it operates on AC, but it is not using that AC, because that AC is 50 hertz only, and it is producing its AC which is at a very different frequency and which is derived from the DC voltages which are converted from that AC from power supply, and then that DC is actually used for this oscillator circuit. So, if I put it on, you have this display which tells how much frequency it is generating. It is generating AC voltages, and that AC voltage is coming here. This is the output point, and finally these are the 2 points. So, here that AC voltage is coming at that frequency which is desired. The frequency can be selected, the ranges, the various ranges are here. So, this is at the range of 100. So, actually this time the frequency is 43 point something. So, it is showing 43 or 44 like that. So, that much is the frequency, hertz, those many hertz, 43 hertz. I can change the units, and if I press this particular button, I had selected another range, and this time it is 4 point something, those many hertz. So, it is producing AC of 4.5 hertz or 5 hertz. So, that is how. Then there are knobs. You can change frequency in more sensitive manner from this knob. The amplitude can be changed from here. All those knobs are there. So, I will just show you that yes, it does produce an oscillatory circuit, and for that we have a unit here. There is a speaker inside, 2 speakers in fact, one here and one here, and then this is a cap here. And if the diaphragm of this speaker vibrates, this will also vibrate. So, let me give this voltage to this this unit, and let me put it here, let me put it here, okay, and just focus here, just focus on this cap. You can see that it is vibrating, and it is vibrating quite, the frequency is quite low. You can see it vibrating, you can count the vibrations, and this is, look at this display, this is 2 hertz. So, that means per second 2 times, and this oscillation, if you count this also, it looks like as if yes, it is consistent, it is per second 2 vibrations or little more. So, that is the kind. If I increase the frequency a little bit, you see it here, I am increasing from 2, it has gone to, let us say, 3, and you can see that this frequency has increased, frequency of this vibration has increased. So, frequency of this vibration is same as the frequency at which this voltages are given, and that is produced by this oscillator. If I increase it further, you can see on the display it is 4, and here you can see it has become faster, the oscillations are faster. This is 10 hertz. So, it is producing frequency of 10 hertz, 12 hertz, and so on. It can also produce frequency of kilohertz, 10 kilohertz, 5 kilohertz, 20 kilohertz, and so on. In fact, this particular one goes up to 1 megahertz. Now to show you a little bit of larger frequency, let me connect it to another unit which is just a speaker, simple speaker. No roll of this PVC pipe at this moment, and with this speaker, if I connect this output, let us see what happens. It's just a speaker here, put this speaker here, and then let me connect my oscillatory output here to this speaker. Like that, vibrations here also there will be vibrations. Now, perhaps you can see this vibrating. It goes up, down, up, down, up, down. Okay, 3 Hz. But I want to show you much larger vibrations. So let me go in the range of let us say 1K here. This is 187 Hertz, 0.186 kilohertz. Can you listen the sound? This diaphragm is vibrating. You cannot see the vibrations because the frequency is so high and the amplitude is tiny. But it is vibrating, and that vibration of the diaphragm is producing sound, and that sound probably you are able to hear in this recording. This is sound at 187 Hertz. If I increase, this 309 Hertz, and you can see the quality of the pitch of the sound has increased, changed. So it is producing those higher frequency oscillatory voltages. This is at 1.368 kilohertz. So likewise 1.862 kilohertz. So this is how the oscillator finally gives you output. So typically, if you look at this expression and use the commonly available inductors and capacitances, and you put those values, then you can see that this omega will be, or this frequency will be in kilohertz region. For example, L, inductor, say let us 1 millihenry, that is the kind of typically of that order. You do not have inductors in henries. If you want to make inductors in henry, it will be very bulky. And similarly, the capacitance is typically in microfarads, 100 microfarad, 10 micro or 22 microfarads, like that. So this is in microfarads. So let us say start with 1 microfarad. So what will be this? What will be this? This will be square root of 10 power minus 3 here and minus 6 here. So if you multiply, it is 10 to the power minus 9, or it is square root of 10 to the power 9. So it is 10 to the power 4 and then multiplied by square root of 10. So this itself is 10 kilohertz. This omega, of course, you have to, if you want frequency, you have to convert it by this 2 pi factor, you divide by 2 pi. So that is 6, that probably will be of this order. So this is around, your frequency is around 10 kilohertz. So in this oscillator that I showed you, it had a low frequency range, high frequency range, middle frequency range. So that LC oscillations that I had described, that can be used in this middle frequency range, which is around kilohertz, 10 kilohertz, 100 kilohertz, like that. So for that, this LC thing can work, but for lower frequencies or higher frequencies, something else will be has to be used, and that must have been used in this box. So Next lecture I will describe one particular circuit which will use these LC oscillations, and that is commonly utilized. Is there for many decades, and that's known as Hartley circuit, or closely related tuned plate tuned collector circuit. So, some kind of circuits, actual circuits which are being used, that I will be describing in next lectures.